So let's try to just focus our mind on this. Remember what we were dealing with before. I actually have the wrong set of guided notes out, so here we go. Okay, so we started 6.2 before the test, and we started talking about these weird things called trigonometric functions of angles, but we didn't really introduce anything yet. All we really did was talk about this thing called the Pythagorean Theorem, and this is a theorem that only works for right triangles, right? What is special about a right triangle?
90 degrees.
Yeah, it has a 90-degree angle, so it usually looks like this. But for this class, I think I'm just going to focus on triangles that are kind of situated this way, but we can situate them different ways, like have the point go to the right instead of the left. And we talked about how we can, if we were given two sides of a right triangle, we can find the other side using the Pythagorean theorem. Okay. We also talked about how we can label different sides of the triangle. So when we have a right triangle, the hypotenuse is kind of the easy one. And the hypotenuse stands for the longest side of the triangle, or the diagonal. Okay. And then we had two other little sides of the triangle, which we called the opposite and the adjacent. Okay. Now, these two sides aren't really like fixed for a certain triangle. It actually depends on what angle we're looking at. Okay. So if we decided to zone in on this angle right in the corner, the adjacent side would be the one next to it. Okay. Now, when the angle is on the other corner, the adjacent side is the one next to it, and it's actually in a different spot, right? We also talked about the opposite side, which is the side that is, well, opposite to the angle that we're looking at. So the opposite side for the green triangle would be down because the angle is up. Okay. So do we have any questions about, oh my gosh, opposite, adjacent, hypotenuse? Yeah.
So on the example, like right on the top of the page, would A be the adjacent, B the opposite, and C the hypotenuse? Or would it be the adjacent?
It actually depends on what angle we're looking at, right? So if we decide to zone in right here, and this is our angle. Oh,
the angle. Is it not when it's like that?
Oh, you mean this one here?
No, let me go back.
Yeah.
I thought that the angle that we were focusing on was the 90 degree square.
Oh, no. So we're never going to focus on the 90 degree. We're just going to focus. Oh, I see what you mean. I see what you mean. Yeah, it wouldn't really work for the 90 degree because, well, the opposite would be the hypotenuse, right? So let's not focus on the 90 degree. Let's only focus on these two.
Okay.
Yeah, that's a good question. Okay. Any other questions on trig functions yet? Okay. Let's go down here. So what we have a definition of these trigonometric functions. So from now on, we're going to be using these functions like x squared or the square root of x and things like that. These are just functions of x. And they have different names like sine, cosine, tangent, cosecant, secant, and cotangent. And they're defined based on the sides of the right triangle. Okay, so for example, if we wanted to take the sine of a specific angle, well, this angle represents the angle that we're zoning in on. So for example, it would be this angle, okay? The sine of that angle is going to be the opposite over the hypotenuse of the triangle, okay? On the other hand, the cosine is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent, okay? So why don't we focus on these so far, the first three. Does anyone remember like something in class? I don't know, maybe in high school you learned to SOHCAHTOA, yeah. I actually didn't memorize it this way, but some people do find it easy to kind of memorize this using this acronym. It kind of sounds cool. So SOH, so sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent is the opposite over the adjacent. So this is kind of a, I don't know, a way you can memorize this. You will have to memorize what sine, cosine, and tangent do mean. Okay. Any questions on sine, cosine, and tangent? All right. Let's shift our focus now into the cosecant, the secant, and the cotangent. Okay. Now, what I want you to do is I want you to look at this page. I want you to compare the sine and the cosecant, the cosine and the secant, and the tangent and the cotangent. What do you notice about these formulas? Yeah, they're flipped on top of each other, right? So the cosecant, oh, yeah, they're reciprocal, good. We actually have a name for this. I'll write this down because Zainab said it. Reciprocal. We use this term maybe in the very beginning of this class, but they're reciprocals of each other, which means they're flipped upside down or they're one over the other, okay? So a good way to memorize cosecant is to just remember it's the reciprocal of sine. The secant is the reciprocal of cosine, and the cotangent is the reciprocal of tangent. Okay. Any questions? Okay. You will have to memorize these, but I think if you remember SOHCAHTOA and reciprocals, you should be pretty good. Okay, so because we talked about these being reciprocals, we have our first set of these things called identities. Identities, these are things that are going to be always true, no matter what, okay? So the definition of identity just means always true. Okay, and this kind of generalizes these guys into something that we can work with a little bit later, okay? Now, we're not going to be focusing too much on these right now, but in the future, we might bring these back. These are called the reciprocal identities because it tells us how sine is related to cosecant. So another way of saying a reciprocal is to say that, well, one is equal to one over the other. So all this is saying is that sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other, and tan and cotangent are reciprocals of each other. Okay, we'll come back to this later, but I have them up right now. Okay, any questions before we go on? Okay, let's try to apply this into something we can actually work with. Okay, so let's just talk about this example. It's telling us that theta, or our Greek symbol here, is an acute angle. All that means is that we're dealing with a right triangle. Okay, that's all that's telling us. So when it says an acute angle, just think about right triangle. It's going to be a small angle. We don't have to think about really big angles here. Okay, and it says that cosine is 3/4. We want to find the values of all of the trig functions of theta. Okay, so what we're going to do is, since we're dealing with an acute angle, why don't I just draw a triangle? Okay, a right triangle, maybe the right angle is here. Okay, and I think it's easier for me to think about when the angle is on the bottom left. So let me just draw theta here. So I just drew an acute triangle. Theta is the bottom left angle. Okay. So based on this drawing, this side is called the what? Hypotenuse. Good. So let me just write that out here. This is the hypotenuse. Okay. What about this side here? Opposite. Good. And I guess the last side is the adjacent, right? All right. So we have all our sides kind of written out for us. Cosine. What does cosine stand for again, using our definition? Awesome. Okay, so since the cosine is the adjacent side over the hypotenuse side, I guess the adjacent is length 3. Let me draw this out here. And the hypotenuse is length 4. Does everyone see how I got that? Okay. Now, since cosine is 3/4, well, we have two sides of the triangle, which is pretty good when we're trying to find the cosine and even the secant. How would I find the other side? Good, the Pythagorean theorem, right? So the reason we even talked about the Pythagorean theorem in the beginning is because we can solve problems where when we have two missing sides, we can always find the other one. Or sorry, when we have two sides that we know, we can find the missing one. Okay, so Pythagorean theorem says a squared plus b squared equals c squared. Okay. Now A and B stand for the legs of the triangle, so not the hypotenuse. So let's just make 3a. Okay. So 3 squared plus b squared equals, well, the hypotenuse is always going to be 4 squared. Okay. 3 squared is 9. B squared, I guess, stays the same. And 4 squared is 16. Okay. I'm trying to get b by itself, so I guess we have to subtract from both sides, right? Minus 9, b squared equals 7. Good. I did this wrong on my paper. Did I? Yes, I did. That's really embarrassing, isn't that? Wait, yeah, I did. Wow, I did that wrong. All right, that's fine. And then taking the square root of both sides, b is plus or minus the square root of 7. But since we're dealing with lengths of a triangle, like we can't have a negative length. So let's just leave that positive. Okay. So we know that the opposite side is the square root of 7. Okay. Now we can kind of go about and try to find these angles. Okay. Now in the question, cosine was already 3/4. So that's pretty easy, right? What do you think the sine is going to be? Awesome. Square root of 7/4. It's the opposite over the hypotenuse. So all we're doing is kind of rearranging the ratio into, well, what was defined. Okay. And tangent is going to be so square root of 7/3, right? Okay. So pretty easy with sine, cosine, and tangent. Okay. Now here's where things get a little bit more tricky. Okay. Let's find the cosecant. Okay. Now the cosecant, remember, is the reciprocal of sine. So what is the cosecant going to be? Good. Okay. Now here's where the problem comes in. Okay. This answer is not fully simplified. Why is it not simplified? Yeah, you can't have a square root in the denominator. So this right here, that's kind of bad, okay? Now, it's not really bad to me when I look at it, but convention kind of says we can't have a square root in the denominator. Does anyone know what to do to get rid of that square root? Not by 2, but close. I can multiply by the square root of 7 to get rid of it, right? But I can't just multiply by the square root of 7. That would change the number. So why don't I multiply by the square root of 7/7, right? Because technically, multiplying by this guy over here is just multiplying by, well, 1, right? Square root of 7/square root of 7 is just 1. So why don't we do this? Okay, and we can multiply across the top and across the bottom. Okay. So 4 square root of 7, I guess that stays the same. What does the bottom become? Not 1, but I think you see that things cancel. Yeah, right? The square root of 7 times the square root of 7 is technically the square root of 7 times 7, or 7 squared, right? So the square root of 7 squared is just 7. So on the bottom, we have just 7. So the whole reason we even multiply by the square root of 7 and the square root of 7 is so those square roots can cancel out. Okay. Any questions here? Okay. Now secant's pretty easy because we already know that cosine is the reciprocal of secant. So all we have to do is flop the numerator and denominator. Okay. Next, cotangent. Same thing, 3 over the square root of 7. But guess what? We can't divide by the square root of anything. So why don't we do the same thing? We can multiply by the square root of 7 over the square root of 7. Okay. When we do this, multiplying across the top, we get 3 square roots of 7. Multiplying across the bottom, square root of something times the square root of the same thing is the thing on the inside. So just 7. Okay. Any questions on how I got these values? Okay. I know I went a little bit fast, so what we're going to do is I have an example that is very similar, except we're working with sine instead of cosine. Okay. Try to do the same thing. I'll be around to look at your answers and we'll come back in a little bit. All right, let's come back together here. So Taylor wrote up some really good answers here. Do you want to take us through what you did here?
So I just drew up the right triangle and labeled the opposite side and the hypotenuse side.
Mm-hmm.
And then use Pythagorean theorem to find the adjacent side, and which was square root of 3.
Mm-hmm.
And then I was just going to tell for the first line across,
Mm-hmm.
and then whenever there's a square root in the bottom, like fix that.
Mm-hmm.
And then for the bottom, I just like flipped all of them.
Mm-hmm.
So yeah, the square root in the bottom, and I just
Awesome. Awesome job here. Let me just kind of talk about the tangent and the cotangent. Perfect job on this one. So with the tangent, I think first when you did SOHCAHTOA, you got 1 over the square root of 3, right? Then Taylor looked at this and was like, okay, there's a square root in the denominator, so I have to multiply by the square root of 3 over the square root of 3. And she got this one over here, right? So technically the tangent, well, it is equal to this number, but it wasn't simplified. And then she got this number here, okay? Next, okay, so after she did the tangent, she went to the cotangent, which is the reciprocal of the tangent. There are 2 ways you can get to this number, right? One thing you can do is take the simplified version and flip it to get 3 over the square root of 3, but then you have to like do all this work to simplify it. So I think what Taylor did is she saw that the unsimplified version was easier to flip to get the square root of 3 instead of flipping the simplified version. Okay. Now I don't care if you flip the simplified version instead of the unsimplified version. However you get to the answer is fine with me. But I thought that was pretty cool how she saw that. Well, you can just flip the unsimplified version. Okay. Any questions on example 4? All right. Okay. So what we're going to do is we're going to make a nice visual of the unit circle. We will be doing something else with these paper plates when we get into sine and cosine and tangent angles based on the unit circle. And I think what I'll do is I'll allow you to bring these to tests and quizzes, okay? So you'll always have this to carry around. So what we're going to do is first, kind of break down your plate a little bit. I know that sounds kind of weird, but just kind of push it down. These plates aren't the best place I could have got, but they're the best to write on. Okay, so once you're kind of done doing that, it doesn't have to be perfect. What I want you to do is I would like you to fold your paper plate into half, okay, like this, and really crease the edges. Okay. Once it is folded into half, I want you to fold it again into half. And then crease those edges as well. Your paper kind of looks like this. Let me zoom in a little bit more on this. There we go. So what we have just done is we have made a unit circle where the axes represent these 2 folds that we made. Okay, so anyone know what this is called? Protractor, right? This is a good, I don't know, it's good to be, oh my gosh. It's a good thing we can use to measure angles. It also has a long side where we can use to draw like long lines and straight lines, right? So what I would like you to do is the best you can. I know it's kind of hard because the plates are kind of crinkly. I would like you to trace with your neutral or black brown marker all the way down the middle on both sides. Okay, so I drew one and I'm going to draw another. Okay. So what we have just drawn is we have drawn the x-axis and the y-axis of our graph, right? So what I want you to do is to label one of these as the x-axis and another one as the y-axis. I'm going to do that here. X-axis and y-axis. So we have our x-axis and the y-axis, and we have this circle that represents the unit circle, right? The circle of radius 1. Okay. So just thinking of degrees here because it's easier, we have 0, 90, 180, and 270 degrees, right? Does anyone remember the coordinates of, say, this point right here at the end? Close. 1,0. Good. I get them confused as well. Okay, so what we're going to do is on the very edge, I know it's kind of crinkly to write on, but the best you can, I want you to label this point here as 1, 0. Oh, yes, sorry. I flipped my thing around. Okay, there we go. What is the point at the 90-degree angle going to be? 0, 1, good. So let's label that one as 0, 1. Next we have, I guess, -1, 0, right? And finally we have, I guess, 0, -1, right? Okay. So why is this backwards? Let's be kind of upset. Oh, we can see it here. That's it. Okay. So what we've done is labeled the x-axis, the y-axis, and the points that represent those on the x and y-axis. Any questions so far? Okay. Before we go on, still with your neutral marker, let's label what these are. Let's start with degrees. So the x-axis right here, this is going to be our 0-degree point, right? Now, another way of saying 0 degrees is 360, right? So why don't we just write 360 at the bottom too? Okay. Now, if we go up to the y-axis, now we're at 90 degrees, right? So let's write 90 degrees. Oh gosh. We also have 180 degrees and 270 degrees. Okay, so just review from our degrees section of the class. Okay. How would I say 0 degrees in radians? 0 and 2 pi, good. Yeah, so 0, nice, you're 2 steps ahead of me. 0 and 2 pi is what that is in radians. Okay. What's 90 degrees in radians? Awesome, pi over 2. So I'll label that. What about 180? Pi, good. And 270 is awesome, 3 pi over 2. Okay. So nothing really new so far. We've kind of been dealing with this before. Let's start adding in our angles. Okay. Why don't we start, gosh, let's start with, let's start with the 45 degrees. I like 45. So what we're going to do is we're going to start with our B marker. Okay. And what we're going to do is we're going to use our protractor. Okay. Now, I think it's been a while since anyone has used a protractor. So what I want you to do is take your protractor and put the very circle in the middle. I want you to put that on the very center of the unit circle. Okay. And then what I want you to do is, I don't know if you can see it, but I want you to align the 90-degree mark with the y-axis. So it's kind of centered. Okay. Now, what I'd like you to do is, as you kind of look across the edge of this, focus on the inner numbers. So the small numbers that go from 0, 10, 20, 30, 40. Okay. And we're going to draw a 45-degree angle. Okay. So I'm going to put a little mark at the 45-degree mark. Okay, so just put a little dot there. Okay. Everyone good? Okay, once you've put your dot, I would like you to take the long edge of the protractor and make a little line from that dot to the center of our unit circle. Okay, once you do that, I want you to finish the line and even connect it all the way to the other edge of the plate. So all the way there. So we've just made a huge diagonal line from one edge to the other at a 45-degree angle. Okay. Any questions? Okay, once we have done that, I want you to put the protractor back in the center. So I want the middle dot to be aligned at the origin. I want the 90-degree angle to go all the way up and match with the y-axis. And what you're going to do is you're going to take a look at the left side of the protractor. What you're going to do is you're going to focus on the outer numbers where they start from 0, 10, 20, 30, 40. Okay, so look at the outer edge, and where it says 45, make another dot. Okay. So you've made a 45-degree angle from the other side. Once you've done that, I want you to do the same thing. Make a line from the blue dot to the center and continue that line all the way to the edge of the circle. Okay. So basically what we have is we have a unit circle and we have our 45-degree angles marked. Okay. Yes, I think what we're going to do, I think we'll do the angles first, and then we'll talk about the points. Yeah, I think that's what we'll do. Okay, so let's take a look at the first quadrant here. We know this is a 45-degree angle, right? So let's just label it as 45 degrees. Okay. Now, you've labeled that as 45. What is 45 degrees in radians? Pi over 4, good. So let me just label that as pi over 4. I'm going to write it kind of small. Oops, sorry, pi over 4. So I'm going to put like the fraction as a diagonal instead. I don't know if you can see that very well, but I wrote the wrong number. I'm very sorry. Okay. And let's just continue that for the other ones. So for example, the second quadrant, I'm pretty sure this is 130, gosh, I'm really bad at degrees. 135, good. 135 degrees, or in radians, 3 pi over 4, right? Okay. Next, the third quadrant, we're at 225, right? Alex is a step ahead of me. I'm cheating by looking at my own. I'm bad at degrees. So another way of saying 225 is 5 pi over 4, right? And finally, the fourth quadrant is 315 or 7 pi over 4. Okay. So we have labeled all of these guys here. Okay. Now, I think what I'm going to do is, well, we'll continue this next class, but let's just finish up the 45-degree angles. What I'm going to do is I'm going to give you a blue triangle. Okay. Now, you're probably wondering why I'm giving you a blue triangle, but we'll talk about this. Okay, 7 pi over 4. 135 is 3 pi over 4. Okay, so you're probably wondering why we have a blue triangle. Oh, you didn't get one? I'm sorry. I'm so sorry. I forgot. I'm so sorry. Okay, now this triangle, if you kind of look at it, it kind of fits right in this little nook here, right? At the 45-degree angle. This is what we call a special right triangle. We're not going to do too much work on these just because, well, we don't really have enough time to go over it. But I kind of want to talk about this, okay? This is a special right triangle. And, well, it kind of talks about, well, a triangle that is used a lot. Okay, this special right triangle has a degree of 45 right here. Actually, the other angle is 45 as well, but let's just focus on this one. It is a right triangle whose degree on the inside is 45 degrees or pi over 4. Okay. Now, there is a way to prove what the side lengths are, but since we're kind of strapped for time, I'm going to tell you the lengths of each of the sides. This is an isosceles right triangle, which means the two side lengths are the same, and they're both length square root of 2 over 2. Okay. I know it's kind of hard to see here. Let me see if you can see it better here. No, not really any better. Okay. So this is a special right triangle. It means that it's just used a lot. It has a 45-degree angle on the end, and well, the side lengths are square root of 2 over 2. If you want to know how I got those values, well, just ask me later in office hours. Okay. So why don't we flip to our unit circle. We've got our x-axis, our y-axis, and we have our 45-degree angle. Okay. Taking a look at this, does anyone want to guess what the coordinates of this point right here are? The x and y coordinates, just like how we have 1, 0 and 0, 1. Well, how far is it out on the x-axis? Not degrees, but maybe like in terms of length. So not 2 pi. Let's take a look at it even more. So I want to know what this point up here is, right? And well, it has to be an x value and a y value. How tall do you think it goes? Take a look at the side lengths of the triangle. Alex? Yeah, right. It goes square root of 2 over 2 up, right? So to get to this point, you would start at the 0. You would go square root of 2 over 2 to the right, and then you would go square root of 2 over 2 up, right? So the coordinates of this point right here, and let me use my blue marker for this, are square root of 2 over 2, comma, square root of 2 over 2. I know you can't see that very well. Let me see if I can put it up here a little bit better. Okay. Okay. Any questions on what I've just done here? Okay. Now, everything else, all the other blue lines, well, they're at the same height of the other one, but they might be in a different direction. Okay. So think about this guy over here. This guy is kind of flipped over, right? But we still have the same side lengths of the triangle, right? So just a question, what do you think the X and Y coordinates of the second quadrant blue line is going to be? Yeah. Mhm. Awesome. The X value is going to be negative since we're in the left quadrant, negative square root of 2 over 2, but we're still going up square root of 2 over 2. Does everyone see how the left-hand quadrant is negative X value, but a positive Y value?
How did you line it up again?
Yeah, so I kind of took this and I flipped it over on its back. Okay. All right, let's just finish up the other quadrants before we go on. The lower quadrant, do you think the X and Y values are going to be positive or negative? Both positive, one positive, both negative? Yeah, both negative, right? This one's going to be negative square root of 2 over 2, negative square root of 2 over 2. And finally, the fourth quadrant is going to be, oh my goodness, square root of 2 over 2, comma, negative square root of 2 over 2. Nice. Okay. So what we're going to do next class is we're going to continue this. So I want you to save your paper plate. I want you to save your blue triangle. And if you don't mind, would you mind putting back your permanent markers before you leave? And we will come back tomorrow in Double Bis 109.